Welcome back to Physical Sciences. I hope you've enjoyed the break. We're going to go on with graphs. In the first session, we looked at the energy profile graphs. We looked at exo and endothermic reactions and the graphs. And we also looked at the rate graphs. So we looked at the graphs specifically from experiments where we looked at the volume over time graph and we looked at the decline in our mass graph. So now we're going to take the time to look at in a deeper detail to the graphs that we get from experiments. Right. So from the experiments, we said there's 3 ways to measure our rate of reaction. We said it's to catch up the gas, so we can go look at the change in the volume of the gas over time intervals, regular time intervals. We can go look at the decrease of our mass over regular time intervals. And if you can remember back then, there was a 3rd way that we can measure the rate of the reaction, and that was to look at the color change that we get, especially when we produced sulfur that made the whole solution a milky color because of the precipitate. So these are the experiments or the experimental way to determine and to calculate the rate of reactions. So if we're going to go look at our first graph, and our first graph is all about the mass of the reactants versus the time. And I need to remind you that because of this decrease in mass, it actually means that we start off at a high mass because at the beginning there is lots of reactant. So at the beginning, we have a very fast rate, and that fast rate goes hand in hand with a very steep gradient. So when you look at it, you see the steep gradient, and then as the reaction goes on and the reactants are being used up, there's less and less reactants, therefore the gradient becomes less steep. And it happens because the reaction is now slowing down. The reaction is still happening, but it is slowing down, and it will go on until we get the parallel lines. And I said to you, if you have a parallel line to the time axis, that basically means that the reaction has stopped at that point. Now, when a reaction stops, one of our reactants, or it can be both of our reactants, is used up. But say, for instance, only one of our reactants are used up, it basically means the reactant cannot any further produce the same products. So at that point where the reactants are used up, we will have a parallel line, and you can actually read that from your axis, from your mass axis here. So when we look at this rate of the reaction, the rate at the decrease of the mass of our reactants, we can actually go and work it out mathematically by saying the rate of this reaction is actually equal to minus the change in the mass over the change in our time, over regular time periods. Now that negative, I just want to explain where that negative will fit in when we do the graph. Now firstly, you need to remember that this gradient that we have here is actually the gradient that will actually be equal to the rate. So if we use the first graph where we look at the decrease of our mass, we can use that decrease of our mass, which becomes our gradient. We can actually use that now to draw a new graph, and that is the graph of the rate of the reaction versus the time that the reaction is on. So if you look at here, let's say we start there, we have an initial mass there. Let's say this is our final mass. So because our final mass is smaller than our initial mass, if we go plug that into our formula, we will have the rate being equal to minus a small number, small mass, minus a bigger number for mass, and that will be over our delta T. So our answer for the change in mass will then be a negative number, and that negative change in mass times the negative in front because of the decrease will then lead to a positive answer, a large positive number. So it's not just large, it's a large positive number that we have here. So if we want to go plot this on the graph of rate versus our time, we will say that first big number can be plotted as a significant number on my vertical axis or on my rate of reaction axis. If we go on and we go work out the tangent line of the gradient, maybe at that point, again we will have an initial mass and a final mass. So because the final mass is smaller, again, we will get a positive number, but the positive number will be a little bit smaller than the first number. So if we're going to do that over time, we will have a plotting point more or less there. And as we go on, we know that as we use the reactants up, we will later only have products. And that will stop the reaction as soon as one of my reactants are used up. So for the last one, where we have that part of the gradient, it will actually equal a 0, which means that we have a 0 point there on our graph. And if we do the line of best fit there, we will get a graph with a negative gradient. We want you to understand where that negative gradient comes from, how that negative in front of my expression is used, and how my mass is actually, the final mass minus the initial mass is actually always ending in a negative mass that we get, and that we plot on the rate graph, and the rate graph has got a negative gradient. Remember, the rate graph comes from the change in mass, that's negative, over the change in time. When we go on to the next one, where we look at the volume that's been caught up in a syringe over time, this is a positive, actually positive, because at the beginning we have a volume of 0. At the beginning we've got lots of reactants, so we know that it is a fast reaction. We know that it is a steeper gradient. So if we go look at our final volume versus our initial volume, we have a bigger volume minus a smaller volume, ending in a gradient that we can plot as well. When we go look at the plotting of this gradient, where we have a change in volume, we still sit with a bigger number, a little bit smaller number, and a number that actually is now equal to 0, as when we get there where the reaction more or less stopped because one of the reactants are used up, when we look at our delta V will be our final minus our initial volume, which will actually be equal to 0, meaning that at that time, with regular time intervals, we will at that time have a volume of 0. So if we go look at the plotting of this, if we go look at this with an increase in volume, even though it is a positive rate expression, we will still see that we have a negative gradient starting from your high positive to your 0. Just look at the unit of the rate there, because we were working with delta V over delta T. We were actually working with centimeters cubed over time, which is seconds, and our unit here will be centimeters cubed per second.
We're about to take another break. Please have a sip of water or some coffee or tea. I'll see you soon.